topic we are going to consider today is internal resistance of a cell. That's one of the topics we are going to consider today. Alright? Internal resistance of a cell. What comes to your mind when you hear the word internal resistance of a cell? What comes to your mind? The opposition to the flow of current that a particular cell offers. That is it. Alright. But this happens right inside. So let us show a schematic representation of what this topic is all about. What we need to do is, first of all, we draw, let me take something better. Where's my chalk? Okay, first of all, we draw a schematic representation of what this is all about, this topic represents, and that is, if we have this to be an external resistance, and then we have this to be the cell in question with some amount of resistance, internal resistance. This represents the internal resistance of the cell. Okay, and we use small r to represent the internal resistance of the cell. E represents the cell itself, that's the energy source, EMF, electromotive force. And then R, capital R, represents external resistance or external load, so to say. Now, what do we do? Of course, we should know that here we have current flow. Somewhere here is switch, okay? Have current flow somewhere here is our key, all right? If this key is turned on, current flows. That's what this shows. If it turns on, current flows. But our concern is the impact of the internal resistance of the cell to the flow of current around the circuits. That's our concern. So what do? We are trying to analyze what happens within the cell. This is the internal resistance. What is the effect of the internal resistance of a cell? The internal resistance of a cell offers opposition to the flow of current as a result of chemical change between the two poles of the cell. Because once the key is turned on or switched on, current flows. As current flows, there is this chemical change between the two poles. But the amount of current flowing into the system is being minimized or reduced as a result of the internal resistance. With this, we can now define Ohm's law within this section, and let's see how we can analyze it to find out exactly what is happening within this section, inside the cell. So if we now define Ohm's law to be V is equal to IR, okay? But because we're making use of E, electromotive force of the cell, we can now represent V with the letter E. And this goes I and then R. This is the potential difference across the external resistance or external load. That's this. Now we can define the potential difference across this as, call this 1, across the internal resistor becomes I and what? Small r. And this is 2. Alright? This is clear. Then the next thing is this. Only one thing, two parameters or two quantities are common. I is common. The EMF or the potential difference is common. But the two resistances are not common. And we cannot define them using a particular formula, which is given as I. The current flowing in the circuit is equal to E all over R plus small r, capital R plus small r. That is it. If we simplify further, we have I, bracket open, capital R plus small r, bracket close, all equals to E. That is what will happen exactly if we simplify further. And then the next thing we are going to have here is redefining it as E is equal to I, bracket open, R plus small r, bracket close. If we try as much as we can to open the brackets, what we have now is going to be E is equal to, for this R, we clear off everything here, we open the bracket using this R, it becomes E equal to I R plus I small r. So with this, we have now come to the point where we now understand actually what happens across the external resistance and what happens across the internal resistance, which happens right inside the cell. So what do? Our interest lies on two things now. One is the external resistance, and the second one is the internal resistance. Two components of concern. The internal resistance, which happens right inside the cell, and the external resistance, which is the external load to the circuit or to the cell. Now let's look at this. If we have IR, this represents the terminal potential difference across the external resistance. This becomes terminal potential difference, right, across R. That's what it means. While this I small r represents the lost voltage or lost potential difference. Okay? Now with this, we now know that actually what minimizes, what impacts the amount of current flowing in the circuit is as a result of the lost voltage across the internal resistance. That's what it means. This lost voltage. Okay? So with this, we can calculate anything. If we now once again recall that E is equivalent to V, we can redefine, we can restate our formula to be V. Okay? We can now say that E is equal to, instead of, oh, okay, let's correct something here. This should be, if we recall that I, R means capital V, right? The terminal potential difference across the external resistance. And then I, R is equal to small v, that is the lost voltage across the internal resistance. We can now conclude and restate our formula to be like this. E, okay, is equal to, instead of IR, we have capital V. Alright? Instead of IR small, we have this becomes plus small v. Okay? Actually, the V we can now see clearly because capital V, potential difference across the external load or across the external resistance. This potential difference across the internal resistance, which is also referred to as the lost voltage. That's the lost voltage. That is why the current is not full. That is why the current is reduced. The circuit is not giving full current because there is this internal resistance opposing the flow of current in this circuit. Once that is well understood, we can still make V, we can make capital V to become the subject here, and we have E minus small v. This is very, very important while solving any question that has to do with internal resistance of a cell. Now we have understood that if we are asked to find the internal resistance the voltage across the internal resistance. Otherwise, we are looking for what? Lost voltage. We are looking for lost voltage. If we are asked to calculate the potential difference across the external resistance, we're also calculating the terminal voltage across R. This should be terminal voltage or terminal potential difference. Terminal PD across R. All right. So with this, the explanation is very, very clear, and we can as well find the value of V using this equation, where we have the energy of the cell minus the lost voltage. And once we have this, every other thing falls into play. One thing we should know is this: the importance of finding this internal resistance is to know the amount of impact the internal resistance have on the current flow in the circuit. Once we do that, we have succeeded in finding out why current is not full when the circuit is turned on. It's simply because of the chemical change between the poles of the cell. All right, I'm going to stop at this point. If there are steps that you do not understand, do me a comment in the comment section, and then I will re-explain or redefine certain terms. For now, I'm signing out, and I hope you're going to share this to your students and your network. See you.